All right, so now we'll continue our discussion in the codes or derivations and code provisions regarding this reinforced concrete beams. Okay, so going back to the figure, um, we have this depth of stress block, then the depth of neutral axis, and then the effective depth, which is um, the depth from the top face to the centroid. So here I'm just showing you a single layer of steel reinforcements. Okay, and for this, um, the width, this beam width, this is designated as B. Okay, so what else? Um, all right, so what's the value of this stress block distribution, this rectangular stress block? So if this is our FC prime, this one would be something like, it must be an equivalent FC prime, but would just rather have to have a different shape profile. So the equivalent would be 0.85 FC prime. Okay, so the 0.85 of this. Okay, so it's just something like that. So just take note once we're doing the calculations when we refer to this stress block, then that's 0.85 FC prime. Okay, so now let's move on to this depth of stress block. So what is this? How do we compute this? So the depth of stress block is equal to this stress block factor beta times the depth of stress block. Okay, so A, which is the depth of stress block, is equal to a factor, stress block factor times the depth of neutral axis. Now the question is, what is this depth of stress block? So this depth of stress block is, sorry, this stress block factor, sorry, let's just write it down. Okay, so stress block factor. Okay, so this stress block factor is actually a function of the strength of concrete. So for example, if we try to look at our figure in our lecture handouts, so we have this figure, I think that's figure 6-10. We have this stress block factor, and then here on the horizontal axis we have the FC prime, and what we get, or the curve that we have, is something like this. Okay, so meaning the stress block factor depends on your strength of concrete. So we have this value, some points here, okay, and then this limiting value. So we have an upper limit and a lower limit. So if our FC prime is between 17 to 28 megapascals, okay, so this is it. So if that's it, then our stress block factor would be 0.85. Now, if we have if we have greater than 28, so here onwards, if we have greater than 28, we have a something like a limiting value. It's actually a range of values from this point onwards up to here. But once we compute um, something like that, it gets into this lower limit, then we have a value of 0.65. Okay, so again, this stress block factor is a function of the strength of concrete. So below this 17, let's say 17 to 28 megapascals, we have a 0.85 value. But if it's greater than 28, then that depends. But the lower limit that we can get is 0.65. Okay, so now what's the value if you fall into this range? So we have an equation, something like this, 0.85 minus 0.05 all over 7 FC prime minus 28, right? So this is our equation uh, if we try to solve it here. But let's say, again, it just means that if we solve a value less than 0.65, let's say 0.5, then what we'll use in the calculation would be the 0.65. Okay, so now let's go to the let's apply the equilibrium equation in the beam. Okay, so let's say this is our okay, so this is our stress block, and then this is our neutral axis, and then this one would be our stresses on the steel reinforcement. Now if you draw the stress profile, what we'll see is something like a side view. Okay, so it's something like this. Okay, we have stresses here. So these stresses, we call it Fy for the yield, let's say yield strength of steel, and then this one would be 0.85 FC prime. Okay, so take note, this 0.85 is different than the 0.85 of the stress block factor. Okay, so although they have the same units, I mean same values, numerical value, they're different. So the ones here, the 0.85 here, okay, that's the equivalent of this parabolic distribution. Okay, so if you transpose this parabolic distribution to rectangular ones, then what we get is 0.85 FC prime. Now, for this value, for the 0.85, this one is the ones that we need when we compute the depth of stress block. Okay, and this value, this depth of stress block, this beta here, depends on the strength of concrete. Okay, so now recall that this is our our depth of stress block, and then this is our depth of neutral axis, and then our effective depth. Then this is our beam width. Okay, so now let's try to apply the equilibrium equation. So we say that summation of forces is equal to 0. So meaning that the compression forces, we can also try to to represent this in terms of force profile. Okay, so let's write it down here. We have a stress profile, and then the ones here will be the force profile. Okay, so what's the difference between the stresses and the force? It's just simply the area. Okay, so here we have this resultant. So since this is a distribution, then we're gonna have a resultant, and since this is rectangular stress block, then the resultant would be just in the midpoint on both dimensions, right? So we have it here. So we have, let's write down C, meaning compression force. So the distance would be simply A over 2. So that's half of this depth of stress block. Okay, and we have this distance, again, it's just the same, the distance from the top face to the tension force, right? So we have tension force, let's say T, that's the distance D, and of course the difference between the D and then this distance would be D minus A all over 2. Okay, so if we try to apply the equilibrium equation, we say that compression force is equal to the tension force. So what's the compression force? So again, if you recall, stress is simply force over area. So if we multiply the stress with the area, then we get the force. So what's the compression force? That's actually the 0.85 FC prime AB. Okay, let me write it down first, and then I'll explain it in a while. Okay, so 85 FC prime AB. Okay, so this is our okay, so this is our um, uh, beam width, and then this is our A, right? Okay, so let me use the color blue, let's say for the stresses. Okay, and we have also stresses here. Now let me use the color green. Okay, I think that would be better. Okay, so we have this A times B. What's A times B? That's actually the area, right? So this is our area, A times B. And then what's this 0.85 FC prime? That's our stress, right? So stress times area, that's our force. Then at the tension side, we have area of steel times the stresses or the strength in the actually that's actually strength of steel. Okay, so Fy. Okay, so from this equation, we can derive the value of the depth of stress block. So A is equal to ASFY all over 0.85 FC prime B. Okay, so we'll put this in a box because we'll use this equation in the analysis of beams. Okay, now we can take another one. So we can take moments, let's say we can take moments, the compression, let's say compression zone, and then what's the moment here. So if you take moments, what we get is, okay, that's the moment, something like a nominal moment. Okay, that's M sub N. So nominal moment capacity of the beam is equal to the tension force. Okay, so this is our point of, let's say, moment or point of rotation. So this is our force, which is the tension force, which is ASFY. Okay, so ASFY times the moment arm. Now, what's the moment arm from tension force to compression force? That's D minus A over 2. So now we can write it here, D minus A over 2. Right, so this is now our equations for the analysis of beams. So we have the depth of stress block, and then we have the nominal moment capacity of the beam. Okay, so let's move on to the strains. Okay, because we still need to apply the load factor that we've learned in the previous topics. So there's going to be some factors here, right? The strength reduction factor, if you recall that. So we have to apply that. So how do we determine this strength reduction factor? Is by the or is through the strains of the RC beams. Okay, so now let's draw again this section of beam, but now we'll show the strains instead of stresses. Okay, so we have this steel area here, and then our let's say our compression area. So this is our neutral axis. Okay, so the strain distribution in reinforcing steel and concrete is assumed to be directly proportional. Okay, so this is directly proportional. Okay, so let's write it here, strain distribution, or let's say strain profile. Okay, so the limiting value for the strains of concrete is 0.003. And then here, the strains of, let's say, the steel, of course, we have to take strain at the of the extreme tension steel. So if we have two layers, that's going to be the strain at the extreme tension steel. Okay, so now let's label the parts. So what's the distance from the top face to the neutral axis? That's letter C. And then the distance from the top face to the, let's say, extreme tension steel, then that's going to be D sub D. Or if it's a single layer, then that just coincide to the effective depth. Okay, so here, this is just simply D minus C. Okay, so it's just simply the difference. Okay, so since reinforced concrete beams are composed of two materials, so since we have concrete plus steel, then meaning we can have, or let's say, or we can have two types of failure. Two types of failure. Of course, that's gonna be related to the percentage or the amount of steel. Okay, so what will happen if our beam section would be, let's say, there's a lot of steel that's put into the section. So what's gonna be the type of failure, and what's gonna be the failure if you have only fewer steels? Okay, so let's write it down. Okay, so let's say less steel, then this one more steel. So if you have more steel, then what you actually the controlling, or let's say the behavior of the beam failure would be something like a brittle failure, because because beam cracks, the failure of the beam is cracking, while the failure of, okay, so I think we'll write it down. The failure for concrete, its failure is cracking. Okay, so that's brittle failure without giving any warning. So you can't see something like deflections or much deflections. You'll just have a rupture. Okay, so that's cracking. Whereas for steel, the failure would be before it fractures, you'll see a deformation. Okay, so it elongates or something like that. So if let's say it elongates, so you'll see a deformation. Okay, whereas concrete, it just cracks. Okay, so if we try to draw it here, something like this. So there's gonna be cracks, the beams. Okay, so if it cracks, then of course some materials will just fall down. Then the entire beams collapse. Now for steel, if it fails, so it's something like it will just bend, right? Because steel undergoes deformation, or steel is a ductile failure, right? So ductile failure. Okay, so if we have more steel, then let's say we put loads, then we the controlling factor would be the concrete, because the steel, they're not heavily stressed because they have a lot of area. So the steel is not heavily stressed, but the concrete is. So once it reaches let's say the maximum capacity of the concrete, then the concrete will fail by cracking. So that's going to be a brittle type of failure. Whereas for steel, I mean, if we have less steel, then if we, let's say, apply the loads, then the concrete, um, the concrete will just be enough. I mean, the the concrete capacity would be enough compared to this steel area. So if you have less area for the steel, then we have higher stresses here. So these ones will be the steel will be the ones to reach the failure. So it's gonna have a ductile failure because it will deform. So the reason why there's gonna be two type of failures or I mean, the reason why we discuss these types of failures, because that's where the strength reduction factors are. That's how we determine our strength reduction factors. Okay, so we have actually um, we have three section conditions. Okay, so we have three section conditions given by the codes. So we have a, okay, we'll just write it here. We have, let's say, a tension controlled, and okay, that's the first one, and then the other one will be the compression controlled, or here we'll just write it here, the compression. Okay, so compression control, and then we have this minimum net, or let's say minimum, oh sorry, I think this one, okay, so this is our tension control, this is our first section condition, then compression control, and then we have here the transition region. Okay, so we have these three regions. So when we say this is tension controlled, so we can just write that as something like steel control. So we have a ductile, something like a ductile behavior. So for compression control, this, okay, so sorry, so this again, tension control steel is the ones that's controlling the section. So it's a ductile behavior. So for compression control, something like concrete controls, and of course this one would be the brittle behavior. So for tension controlled, we can say that steel yields before concrete crashes. Okay, so that's why it's going to be ductile behavior. So steel yields, so steel reaches its limit before concrete. For here, for compression controlled, we have concrete cracks before steel yields. Right, so now if we try to draw the strain diagram, it's something like this. So we have our, or we'll just draw it here. Okay, so tension controlled. Then we have compression controlled. Okay, so for the strain diagram, something like this. So this is our neutral axis, and this is our strain of concrete, which is 0.003, and then our strain on the steel would be greater than, let's say, greater than 0.005. Okay, so that's the definition. Okay, so before we discuss these details in the compression control, I think we'd rather, or I'd rather show you the graph for this strength reduction factor, because that's the reason why we're actually doing the strain derivations, because what we're after actually is the strength reduction factor. Okay, so here we have the V, which is the strength reduction factor along the Y, and then along the X would be the strain value. Okay, so the value of this strength reduction factor depends upon whether you have a transition region or tension controlled region or compression controlled. So we have this graph like this. Okay, so here Okay, we'll just use the color blue. Okay, so here we have a 0.005 strain, and then here let's say we have the yielding strain. Okay, so from this 0.005 onwards, that's what we call the transition. No, sorry, that's the tension controlled. Right, it's tension controlled region. And then below this yielding strain, that's going to be the compression controlled region. Then of course, between this would be the transition region. Okay, so it just says, the graph just says that if you are in the tension controlled region, then what you'll need, or the strength reproduction factor, would be 0.9. But if you are in a compression controlled region, you're gonna have value of 0.65. Okay, so that's the value. If you're in compression controlled, this is it. If you're in tension controlled, then 0.9. But if you are in between, let's say you're in the transition region. So how do we know if you are in tension controlled, or in compression, or in transition region? We gonna determine that if we do the calculations for the strains. Okay, so we'll discuss that in a while. So for now, how do we know if what's your reduction factor if you are in this transition region? We have an equation, 0.65 plus, okay, strain in the tension steel minus yielding strain, and divided by 4, 0.05 minus. Okay, so we can solve it. Okay, so you can solve. So of course, this value, if you're in the transition region, will just basically between this range, 0.65 or 0.9. Okay, so that's the upper limit. This is the lower limit. Okay, so now how do we compute our strain? So for the strain, recall that, okay, we'll just use this one. Okay, so we have this distance, right? So this is our depth of neutral axis, and then this is our depth, effective depth. Of course, that's to the centroid. So if that's the extreme tensile extreme tension steel, okay, we can just write d sub t. Okay, so the difference between this effective depth and this depth of neutral axis would just simply be d minus c. Okay, so now we can actually solve for this. We can solve for this extreme tension steel. Okay, so forget about the 0.005. That just refers to the tension controlled regions. Okay, so this is what we're actually trying to solve, this E sub D. Okay, so how do we solve that? So we can do a similar triangles. So this one divided by this, let's say, this opposite side divided by this adjacent side, then is equal to this opposite side divided by the adjacent side. Okay, so we'll do that, and what we get is 0.03 all over C is equal to E sub D. Okay, so now if we cross multiply, we get is 0.03 D minus C is equal to, and then further on, we can rearrange. Okay, so I think you can just rearrange that, and what we get is something like this: 0.003 E sub D plus 0.003. Oops, not that one. We're actually trying to solve for this. But if you're trying to solve for this ratio between this depth of neutral axis and the effective depth, this is it. But for us, it's gonna be Okay, you can just rearrange 0.003 d minus c all over c. Okay, so this is the equation that we will need for our calculation, right? So for the strain, so how do we determine the strength reduction factor? So we have to solve for this strain value in the extreme tension steel. So once we determine our strain in the steel reinforcement, then we can determine if it's in the tension control or if it's in compression control, and then we can determine our strength reduction factor. Okay, so there's one more about the minimum reinforcement, steel reinforcement. So the code also requires that there's going to be some minimum area, steel area. So we have a maximum of the two conditions. So we have square root of fc prime for fy times the beam width times the depth. Okay, so you can just say b times d, and then this one 1.4 pd all over fy. Okay, so whichever is the maximum, that's going to be our minimum as. Okay, so take note, this is just minimum. If it just means that if your computed as mean is below this value, then you have to provide this minimum area. But if your value is above this minimum, then that's fine. Okay, meaning that the code requirement is met. Okay, so our next video will be sample calculations for the analysis of simply reinforced beams. So our procedure for analysis is also given in our lecture handouts, but I'll just discuss it in the next video. Okay, so see you in the next video.